All right, we're back. So 10.2, chapter 10, part 2, is all about this thermodynamics thing that I mentioned before. So thermodynamics is the more like general version of thermochemistry. So thermodynamics is talked about in chemistry and physics and maybe even biology. Thermodynamics studies the relationship between heat, energy, and work, and the conversion between them. Not necessarily in chemical processes, but in general, heat, energy, and work, and the conversion between them. And we're going to talk about 3 different types of systems. So we already distinguished between systems and surroundings, but now we're going to talk about different types of systems. So there's an open system where both energy and matter can be passed to or from the surroundings. So energy and matter can go in and out of the system freely. There's a closed system where energy can go in and out of the system, be passed to or from the surroundings, but matter cannot. The matter has to stay inside of the system. And there's isolated systems, where neither matter nor energy can be passed to or from the surroundings. And these are some pictures of that. So this one here on the left is your open system. You can tell because it's, open at the top. And both energy and matter can escape from this system or go into this system. So the heat is our energy part. So heat can flow in or out of our glass container. And water vapor is our matter part. So these molecules of water, gaseous water, are escaping from our system and they're going out into the world, into the universe of our surroundings. This one's our closed system. It's got a cap on it now, cork, whatever. And so now the water vapor can't escape. Our matter cannot escape or, come back in. Only heat. So glass is not a very good insulator. Glass, gives off, lets heat escape pretty easily. If you touch hot glass, it's pretty hot. It doesn't keep all the heat on the inside. It just comes right out and burns your hand. So closed system, but not isolated. This one is your isolated system. So it's got this insulator, this layer of insulation, keeping all of the heat inside the container, inside the system. So now matter can't escape, neither can your heat energy. Or it can't get in. So it just depends on what you're thinking about. So if you have a hot cup of coffee or a hot thermos of coffee or tea or whatever you're drinking, hot chocolate, that you don't want the heat to get out. You want it to stay hot. But if you have, a water bottle, then you probably want that to stay pretty cold. Not a lot of people like drinking hot water. So it just depends. Insulation works both ways. Keeps heat in or out, ideally. All right, so another thing to consider with energy is that it is not really a relative thing. It's something called a state function. So energy, pressure, volume, and temperature, they're not the only state functions, but they are examples of state functions. And what does that mean? A state function is a property of the system that depends only on its present state. So the temperature of something doesn't depend on what temperature it was 10 minutes ago or what temperature is going to be in 10 minutes. The temperature only depends on what temperature it is at that time. Same with volume and pressure and energy. They depend only on the present state of the system. Likewise, changes in state functions depend only on the initial and final states. They are independent of the transitions between these states. And that might not make any sense to you right now, but let's look at an example. So this is an example of maybe your dorm building. So say you live on the 4th floor of your dorm, and you have to walk up several flights of stairs to get there. So the change in elevation, how high you are off the ground, doesn't depend on, how many flights of stairs you took. It doesn't depend on if you went up to the roof to like take a good look and then came back down to the 4th floor. Doesn't matter. Your change in elevation is the same no matter what. It's just dependent on the distance from the ground of the 4th floor. So elevation is a state function in this case and in general, whereas the distance you covered is going to depend on, or like the number of steps, I should say, not the distance. The number of steps that you took depends on the pathway. So if you only go up to the 4th floor, you don't want to take a look off the roof today. You had a long day and you just want to go home, then you have, this many steps. Say it's, I don't know, 30 steps. 10 steps to go up to the 1st floor, another 10 to the 2nd floor, and then, 10 steps to go from the 1st floor to the 2nd floor, 10 to go from the 2nd floor to the 3rd floor, and another 10 to go from the 3rd floor to the 4th floor. That's 30 steps. But if you did go up to the roof and take a look, that's another 10, 20, 30, and then back down, 10, 20, 30. That's an extra 60 steps. So the number of steps does depend on your path, whereas the change in elevation, again, or the distance from the ground, doesn't change. So that's an example of state functions for you. Energy is a state function. It's the one we're going to talk about now. So energy doesn't depend on states 2, 3, or 4. It only is going to depend on states 1 and 5. If we're transitioning between states 1 and 5, the energy difference is going to be whatever 5 minus 1 is, not 2 minus 1, 3 minus 2, 4 minus 3, 5 minus 4, all added together. Nope, just 5 minus 1. Anyway, the first law of thermodynamics. So now we're gonna learn some new things. It sounds really fancy, right? The first law of thermodynamics. All it means is that the energy of the universe is constant. So just like matter, you know how we said there's a law of conservation of mass, there's a law of conservation of energy too. So just like mass, energy is conserved. It is neither created nor destroyed, but only transformed from one form to another. One form of energy becomes a different form of energy. It is never created or destroyed. Energy of the universe stays the same. But it's impossible to measure the energy of the universe at any point in time. So instead, we measure energy changes of the universe, or usually it's easier to measure energy changes of a system. So energy within a system, so this within a system, the internal energy of a system, we call U. And we can't measure U, but we can measure delta U. And that's where that state function thing comes in. It's just UF minus UI. So we use U for internal energy to differentiate it from E, because E was for things like particles, electrons, photons, whatever. We are talking about internal energy of a whole system. So a, solution or something, not just the individual electrons or particles inside of that system. We are talking about the internal energy of the whole system. All right, and the internal energy of a system comes in many forms, and is generally classified as these two types of energy we've seen before: kinetic energy and potential energy. So kinetic energy is related to motion of things in the system, and potential energy is related to interactions, so specifically electrostatic interactions. So now we're talking about the internal energy of a system. So this is specific kinetic energy, not just you rolling a ball down a hill, but the kinetic energy in a chemical system. We're talking about the movement of molecules, translation of molecules, rotation, vibration of the bonds in a molecule. You'll learn about that more in a little bit in organic. So that's the movement of molecules, these different types of movement, as well as the movement of the electrons within the molecules. So movement of molecules and movement within molecules, but movement in general. The potential energy of the chemical system, the potential energy in a chemical system involves electrostatic interactions. We've seen these before. Electron-electron repulsion, nuclei-nuclei repulsion, electron-nuclei attraction, and also interactions between molecules, otherwise known as intermolecular forces, or IMFs, from chapter 7. Both of these types of interactions, these electrostatic interactions, which is typically what intermolecular forces are as well, both of these types of interactions depend on position. That's what potential energy is usually based on. So these interactions depend on position because of Coulomb's law. So we love Coulomb's law, and we don't actually need to talk about it too much here, but that's the behind the scenes. All right, so let's look at the energy associated with a chemical reaction. So this one's from your book. We've got sulfur, so solid sulfur, which doesn't smell very good if you didn't know. Smells like rotten eggs. Sulfur plus oxygen gas is going to form sulfur dioxide, which is a different gas. And we're going to talk about the energy associated with this reaction. We don't know the internal energies of these reactants or this product, but we can measure the difference. We can measure that energy change as a result of the reaction. So we don't know the internal energies of any of these three things, but we can tell the difference in energy from the reactant side to the product side. We can measure that in the lab, and we'll talk a little bit more about that with Nick's lecture next week. Anyway, this change in energy, delta U, is equal to the U, or internal energy, of the products minus the internal energy of the reactants. So this is our, final minus initial. Products are what we end up with, so the products are the final, and reactants are what we started with, so they're the initial. So delta U is equal to the energy content of 1 mole of sulfur dioxide minus the energy content of 1 mole of sulfur and 1 mole of oxygen gas. So combined, the energy content of our reactants combined. So that energy difference from reactants to products is negative 296.4 kilojoules, which, because it's negative, means that our reaction gives off heat. It is exothermic. So exothermic, if you remember, is one that goes from a higher energy to a lower energy. So our products are lower in energy than our reactants, and that's why we get a negative energy change. So say this here number is 1, this energy, it's not 1, but say it is, and say this is 100, then our energy difference is final minus initial, 1 minus 100, negative 99. So it's always going to be negative if we're coming from a higher energy to a lower energy. If our reactants have more energy than our products, we're going to release energy. We don't need that energy in our reactants anymore, so it is going to come out and go into the surroundings. So it's an exothermic reaction when the reaction is considered your system. Okay, so that was a change in energy for this system, this reaction, but the energy of the universe is still constant. Remember that has to stay the same. That is our first law of thermodynamics. So how does that work? Well, the energy of the system plus the surroundings is equal to the energy of the universe, or the change. So yes, but also the change in the energy of the system plus the change in the energy of the surroundings is equal to the change in the energy of the universe. So either the constant states or the change, they're equal. Because if you remember, our system is the Earth in that one example, and our surroundings is everything else. So if we're talking about the universe, the Earth is included in the universe. So we need to add together our system and our surroundings to get the universe as a whole. So the first law of thermodynamics says that this is equal to 0. There's no change in the energy of the universe ever. It's just transforming into different forms of energy. So the change in energy of the system and the surroundings added together is also equal to 0. And if we rearrange that equation, we find out that the change in energy of the system is equal to the negative change in energy of the surroundings. And that actually makes a whole lot of sense if you think about it from like a common sense standpoint. The energy that your hand is providing to the ice cube for it to melt, that energy is going into the ice cube and coming out of your hand. So your hand's getting cold because it's losing heat to the ice cube. And the ice cube is gaining that heat. So the energy goes out of one thing and into the other, out of the system into the surroundings, or out of the surroundings into the system. It doesn't go anywhere else. There are only those two options. Alrighty, so back in chapter 3, we learned the definition of energy was energy is the capacity to do work or transfer heat. So we've talked about this transfer heat part. We haven't talked much about the work part yet. So work, we're going to call W, makes sense. Heat, we're going to call Q, doesn't make as much sense, but that's fine. And the internal energy of a system is equal to the heat of the system and the work of the system. So remember, heat is actually a transfer of thermal energy. So Q is actually a change, just like this delta U over here. Work is the same way. Work is actually a change. It's the transfer of energy from the system to the surroundings or vice versa via mechanical motion. So these are both actually changes, even though they don't really look like it. So delta U is equal to Q plus W. So heat plus work equals energy. So Q is, like I said, our heat that is transferred between the system and the surroundings, the heat flow between the systems and the surroundings. And work is, or W is work done by or on the system. So let's take a look at that. What does that mean? What is our convention here for science? So, all right, let's look at the first one. Heat is absorbed by the system. It's an endothermic process. This is your ice cube. The ice cube is absorbing the heat from your hand. So the ice cube is absorbing that heat and melting. The melting is an endothermic process. So keep that in mind. That might be important later. Melting is an endothermic process. And because the heat is going into the system, Q is positive. So the heat is going into the system. The energy of the system is going up because it's getting heat. So Q is positive. Likewise, when heat is released by the system in an exothermic process, so you're burning wood, so the wood is giving off heat, or the fire really is giving off heat, so it's an exothermic process, and the heat is flowing out of the system. So you are warming up, but you're the surroundings, remember? So when you are warming up, the fire is giving off that heat. So the heat is leaving the system, so it's negative. All right, and work. Let's look at work. So work done on the system by the surroundings is positive. So when volume decreases, work is positive. So it's easier to look at a picture. We have a picture down here. The surroundings is doing work on the system. Work is being put into the system. When something's going into the system, like heat is going into the system for an endothermic process, it's being absorbed. Heat is going in, Q is positive. Work is being put into the system. I mean, it doesn't really look like that. Work is being done on the system. You can think of as work is being put into the system. And when you put stuff into the system, it's positive. Work done by the system on the surroundings, the volume increases, so the work is going out of the system. The volume is expanding, going out of the system, making the system bigger, going out. Work is being done by the systems on the surroundings. Work is going out, so work is negative. So these are our two conventions here. When heat goes into the system, Q is positive. When work is done on the system, W is positive. And because both of these are positive, delta U is positive. When heat is leaving the system in an exothermic process and work is being done by the system, then things are leaving the system. So Q and W are both less than 0. They're both negative. So delta U has to be negative because it's the sum of those two things. Now, when one of them is positive and one of them is negative, they could cancel out. But this is how this convention works. It works because of this definition of delta U equals Q plus W. And that's pretty much it. So I'm just going to give you guys a summary slide. This is another way to look at heat and work. I don't know which one will be more effective to sink in for you. This should be delta U, delta E. This is from an old book, sorry. So you can use this slide to help you remember the sign convention or the other one. It doesn't matter. They're both the same, just maybe worded a little different. The picture's a little different. Thought I'd give you both options. All right. I'll see you guys tomorrow. Have a good night.